So today's question here, folks, is on the 2018 free response questions, question 5. And this setup basically shows you a spring system, right, in which we drop one block on top of another while this spring system kind of goes into motion. So reading the actual prompt here, though, rather than just kind of speculating in the picture, it says block P of mass M, block P, so we're talking about the bottom block here, right, is on a horizontal frictionless surface. Okay, so that means that we're not going to have any kind of energy lost here. It should be like where maybe your mind jumps to. And, technically speaking, in this idealized system, this thing should keep going. It shouldn't stop moving. And it's attached to a spring with a spring constant K. Okay, so we already know that we're getting to some spring stuff here, right? We know we have some sort of spring constant K. If the spring itself wasn't a big enough clue, right? The fact that we're getting a constant should hint you towards some of your spring equations. It then says the block is oscillating with a period TP. So not toilet paper, but TP as in the period of our spring of, or the period of block P oscillating by itself, right? With an amplitude AP about its spring's equilibrium position, X naught. Okay, so this is actually also important. So X naught is our equilibrium, meaning it makes it to some distance. Let's call this, AP, right? Because if this is our equilibrium, right, it's delta X that would be like our amplitude there. AP is the furthest stretch from equilibrium that it experiences. That's what it means to be an amplitude, right? The largest stretch of a spring oscillator. It then says a second block, Q, of mass 2m. Okay, so now we're getting some information about the second block. Is then dropped from rest and lands on block P at the instant it passes through the equilibrium position. It immediately sticks to the top of block P, and the two block system oscillates with period TPQ and APQ. So it basically, when this thing finally does fall, it sticks instantaneously, almost like it's dropped, right? It sticks perfectly at the equilibrium position, and then this thing continues to oscillate. So really, what did we effectively change here? We affected the mass of the system. And the question is, how will this mass probably affect the rest of the stuff? And so when we do finally fall on top, we know that we get a new period. This is called TPQ. And potentially a new amplitude, right? APQ. Those are two things that we're given. Now, as we kind of continue with this, right? I'd normally like to, at this point, speculate a little bit, but let's read the problem prompts first before I speculate too much, just to kind of show you how you'd go through solving this problem. So it says, determine the numerical value of TPQ over TP. Okay, so we now need to make an expression. Ooh, why is that drawing with my finger? Oh no, that's not my pen. This is my pen. There we go. That was weird. Okay, so in looking at this, right, we might want to write an expression for TP first using the values here. And that might recall, or you might recall, that the period of a spring is equal to 2 pi square root of m over k. Now for TP, our mass was just m, right? Our spring constant's k. So nothing is going to kind of change there. And Jonathan, we'll check to see if your answer is correct in just a moment. But I'd like to kind of continue discussing how we get through this. Ooh, sorry, dogs. So the next part here is then TPQ, right? So what changes for TPQ? Well, in this expression, our spring constant doesn't change, right? That's inherent to the material itself. So K on the bottom should be the same. But my new mass is now what? Is it just M? No. 2M? No. What would it have to be? What would be our mass here when we drop block Q on top of block P? 3m, not to be confused with tape brand, right? So 3m is going to be our new value for our mass here. Oh, come on, cat. Can't do this right now. There we go. Sorry. I'm getting interrupted this morning. But so these are our two expressions, right? So now what do we want to do? Well, we want to find a way to make a ratio of said um, things and try and deduce, based upon creating a fraction, what this relationship really is. Um, so as we do this, right, we have to then see kind of what will cancel, what won't, and how we can kind of simplify this expression, right? Um, what are some things that we can do to simplify? So first off, what are we actually doing? We're taking TPQ, right? And we're dividing it by TP. So when we do this, we have to write out the full expression, right? Which is 2 pi square root of 3m over k divided by 2 pi square root of m over k. This requires some knowledge of like our rules for radicals, because I think what's easy to start off with here is to cancel out the 2 pi's, right? Those are not relevant in this problem. But when I take two things that are in radicals and I divide them, right? What can we do to kind of rationalize these things, or what can we do to like kind of deal with these radicals? What can you do? What would be another way to like rewrite this? I guess it goes back to a very basic like radical rule, right? If two things are raised to like the 1/2 power, right? You could square the whole thing. You could get the ratio of the squares and then square root it in the end. But really then you're just going through the same process, right? Because either way, you don't want the ratio of the squares, you want the ratio of the actual things. So you could remove powers that way, right? But technically speaking, right? Can I rewrite this expression as really this is just like, let's say I had x squared, right? Times 2 squared. Couldn't I just write this expression as like 4x squared? Meaning, if I have like 3 to the 1/2 power and m to the 1/2 power, which is really what a square root is, and they're multiplied, I can put them in. I can say that that's really the same kind of thing going on there. So if it helps you, you can square it first. But we're going to basically just kind of go back and forth here. But let's say we squared both sides, because you're right. Technically, you could do that. What would this do? Let me go with Hong's approach here, because this is what he was thinking of. If I square both sides here, right, and I multiply both things by themselves, what do I undo? I undo all of the radicals, right? Because when I square now this whole thing, right, I'm just multiplying it by itself. So then what we'd have is that TPQ squared over TP squared is equal to 3m over k divided by really like 1m over k, right? Which then if I were to like cancel out here, I can cancel out my m over k's. And then what could I do? I could square root both sides, right? And as a result, what's really our ratio, our numerical value of the ratio? Well, it's 3 to 1 is the ratio of the squares. But then when I square root it, it's really rad 3 to 1, right? Because the square root of 1 is just 1. So as a result, this is kind of what you're going to end up with. This is TPQ over TP, right? You got to square root the result that you got here. You got to square root both sides. So I think that's not a bad approach, right? If you square both sides, you can quite easily kind of undo your radicals, solve it that way, and then solve back. But what if we had noticed like radical rules? Like what could we have just done there? We could have just factored out the coefficients rather than just saying it was square root of rad 3 m over k. We could have just said it was it was rad 3 times rad m over k, and then it was 1 times rad m over k, and canceled out the m over k's, the rad m over k's, right? And then it's still just rad 3 over 1. Anyway, so that's our part A. right? Now we need to jump down um, to our part B, which says the figure is reproduced above, right? It's just so that you can see it again. And then it says, how does the amplitude of oscillation, APQ, of the two block system compare to the amplitude AP of block P alone? And it says, in a clear, coherent paragraph length wow, I can't speak. Paragraph, para, paragraph, paragraph length response that may also contain diagrams and/or equations. Explain your reasoning. Um, wow, I was so tongue-tied there. Now, what can we do here? So what do we have to say? We have to say now when we add mass to the system, how does that affect your amplitude and why? Will they be equal? Will one be less than? Will one be greater than? These are things that we got to think about. Um, and what would you think about this whole thing? Like, where does your gut tell you that? What would we think of kind of to start here? Anyone have any like glaring thought process here? Like, oh, it's got to be this answer. Won't it be the same but slower? Um, what's happening here when I drop this thing on top? Right? We had a block M that was moving with a certain speed, right? A maximum speed at the equilibrium. How will that maximum speed be affected if I now just increase the mass? It won't be the same amplitude anymore. And there's a few different ways that you can think about it, but I think there's like one very like concrete way to think of it. The max speed will now be slower. What does that mean then about your oscillation? If your speed is slower, then the spring will be more easily able to accelerate you to rest, right? How will that affect your amplitude? Yeah, Fish, I like that. AP has to be greater than APQ. I like that a lot, right? So AP is the oscillation with just, right? This was like the maximum displacement with just, block P. APQ is now when we have both of these kind of tied together, right? P and Q. And APQ is going to be something less. Now, I don't know how much less exactly, but we could probably actually deduce that if we really wanted to go through the algebra of it all. But we don't have to explain that in this question. We just have to explain why it must be less. So let's address some key things here. So I like that we're on the right track here, and this is indeed the correct choice. AP is greater than APQ. Now, the question really comes down to what physics phenomena best describes this. And let's establish some like concrete things that we know. We know that since this is the equilibrium position, this is the max V, right? And we know that that V is related to our kinetic energy at the max point, right? But we know that the kinetic energy at the maximum point or as we move through equilibrium must be equal to the potential energy max. And really, now I've written an expression here that says 1/2 m times v squared must be equal to 1/2 k times x squared. Now, rather than writing x, though, I'd prefer to actually write a squared. Why? Because that x, that potential energy max, that x value is the amplitude, the furthest that you are. So if we now have an expression that relates the energy here, right, that the Ke max must equal the Pe max. The question then comes, how can I tie that back in? Because this is actually like the middle of the explanation, believe it or not. This still doesn't address this key fundamental issue of why do I know that when I drop 2m on top of m, why do I know that our new v is smaller? How do I know that this v is smaller? What law? There's a law here. What law tells me that it must be smaller? I'll give you a hint. We're dealing with two objects, right? We started with one object that was moving, and we just simply added more mass to that object. So really, if you just think about quantifying its motion, right, you had a mass moving at a certain speed that now has increased mass. How will that have to affect their speed and why? Yeah, Jonathan, you got the right idea here. It's momentum, right? We know that mv, using v like with just block p attached, right, must equal 3m times our v with block p and q. Because really what's happening here is we effectively just had a collision, right? So technically speaking, this actually gives us an expression for how much larger VP was than VPQ. But in fact, right, if we had just mass m and now we have mass 3m, right, you could actually deduce that VP is 3 times as large as VPQ. But if we had 3 times as much speed, right, how would that impact the kinetic energy? Well, once again, I'm going a little bit further into the mathematical reasoning than you actually had to do for this problem. But I could actually make an expression that says that I could actually relate AP to APQ by plugging in for the mass value and the speed squared value, right? And kind of deducing a coefficient, right? This would be 1/2 m times 3, and this is, VPQ, because we're going to keep it in terms of VPQ squared. So we end up with a factor of 9 out in front. So this is 9 times 1/2 mv squared, right? Is related to 1/2 k times AP squared. But for the other block, right, we now have 1/2 m, or rather not 1/2 m, 1/2 3m times, VPQ squared, which as a result only gets a factor out now of 3 times 1/2 mv squared. And that's going to relate to APQ squared, right? So 3 times 1/2 mv squared is equal to 1/2 k times APQ squared. Or as a result, right, the amplitude, I actually now know definitively that the amplitude is a third of its previous value as we relate this. Actually, no, the square of the amplitude is a third. So is it just, how would we do that? Would it just be rad 3 of its original value? Meaning we'd have to actually solve this for now APQ. But that, once again, mathematically, like what I would have to do here is I have to compare this equation right here. I'll box this in to this equation to deduce how AP relates to APQ. The 1/2 K's would cancel if I divided them, right? If I get a ratio, I divided them. And then the 1/2 MV squareds would cancel. So AP squared over APQ squared is equal to 9 over 3. But 9 over 3 is just 3 over 1. So the ratio there is rad 3 to 1, right? So if you were to get like a numerical value, I guess maybe it would be better to do it the other way around. 1 divided by rad 3. You would get 0.577. So it's going to be a little over half. So like if this was, if I'm trying to visually cut this kind of region in half, it's going to be about 0.6. Would be where APQ is. Now, did you have to do that? No. What do you have to explain? You have to say, due to the law of conservation of momentum, we know that the speed through the equilibrium will be decreased for the oscillation of blocks P and Q. As a result, right, this will change the maximum kinetic energy of the system by decreasing it as well, right? Which will then affect the potential energy of the system. potential energy of the system is directly related to the amplitude squared. Yeah, let's do it. Let me write this out. So as a result of dropping, or actually of as a result of, maybe not dropping, maybe I should say as a result of adding mass to the system, the speed of blocks P and Q must be less than the speed of block P for the two systems at equilibrium. This must be true to satisfy the law of conservation of momentum. Now you'd have to get into like kinetic energy, right? So this in turn, or the decrease in speed, would reduce the kinetic energy of the two block system I should probably say the maximum kinetic energy. I'm gonna actually squeeze in there the max kinetic energy of the two block system. And as a result, actually, and well, should I just end that sentence there? I don't want to make this a run-on sentence. This would in turn decrease the maximum potential energy of the system. And I would even probably put here in parentheses, Ke max is equal to Be max. This is kind of implying that you know that since there's no friction, that's not going to be decreased. And then I guess my last statement here would be about how that potential energy of the system actually relates to the amplitude. And I would say potential energy max, right, relates to 1/2 K A squared, right? Therefore, a decrease in potential energy will result in a smaller amplitude. So I changed colors actually for a very specific reason. My green, because you could probably simplify this in fewer words. This was me just kind of rambling off the top of my head. But the green hits one very key term, right? Conservation of momentum, right? This is just looking at momentum, P. Whereas the blue, or rather the red, focuses on conservation of kinetic energy, right? KE is equal to PE. And it also ties together, in the red, I also tied together how P was related to really my, my kinetic energy here, right? Um, then the blue relates the potential energy to the amplitude of the system, right? Or to A squared to be more specific, but then tells us why it's actually going to have a smaller amplitude. So we go from momentum to energy to amplitude of a simple harmonic oscillator. So those three very key ideas are needed for this explanation. Okay. Rather than going into the second problem today, I think actually I'm going to leave that circuit question for you guys to actually do for some homework. And I think what I'd like to do instead with our time here is I'd like to look at some sample responses and look at the grading rubric um, for, let's start with that question that we just did. Maybe that would be a good one to just look at. And then we can see if we want to kind of continue looking at some of these as we go on. So I'm going to actually stop sharing my tablet screen. And I'm going to show you my other screen in terms of how we share this. I'll share the screen right here. Okay, share, boom. All right. So I wanted to, continuing that thought, I wanted to show you how we can kind of look at the way an AP grader would look at this question and some of the things that they'd look for. So here on my other screen here, you now kind of see the same question that we just looked at. And for this first question, they simply give you, for a correct answer of rad 3 is 1 point. And if you notice, wow, the grade distribution for this question seems to be heavily weighted towards part B. So out of the 7 points for this question, right? This is out of 7 points total. Now to give you guys an idea of the point system for this test, like in terms of your points, your smaller questions are always worth 7 points, and then your longer questions are worth, if I remember correctly, I think it was like 13 points. Let me see. Or 12 points. You have 7 and 12, right? There's typically 2 longer questions in a test and then three shorter questions in terms of like a constructed response segment. So 3 times 7 is 21, right? 2 times 12 is another 24. So you get about 21, 24, like 45 points associated with this, right? And that's just kind of like a rough breakdown. Then the multiple choice, which you typically would have like 40 graded questions, they also factor in 10 ones that weren't graded, would be, I guess, if you gave them a point apiece. I think the raw score, usually the raw scores, they still calculate out of like 40 points, so that they do 40 and 40 to basically give you like a total out of 80, whatever it is, to get like then your raw score. So regardless, though, looking at this question that would be normally worth like 7 points, which is still a significant amount, they only gave you 1 point for doing this first part. That first part where we went through all of that work to figure out what the ratio of TP to TPQ was, or the reverse of that, it's just 1 point, and you just had to have the correct answer. It's a little disheartening when you think about it, because there still is some thought that's required in that, and we're taking the ratio of those 2 fractions. However, for part B, they actually break this down into several different stages, right? So note the response is graded even if an incorrect selection is made. So basically, you could have checked the wrong box for one of these, and you're still going to get a grade based upon your explanation, right? Um, so realize that looking at this, we would have gotten a point, right? Because we applied the conservation of momentum to the collision, right? we basically said that, okay, well, momentum must be conserved, and we talked about how that led to a decrease in speed. And then for correctly finding that the post collision speed has decreased. So not only applying the law of conservation of momentum, so just having stated, this is a collision, therefore momentum must be conserved is a point right there, without even explaining how that actually impacts the system. We're then correctly applying it by saying, okay, wait a second, you've decreased the post collision speed. You get another point. So that's 2 points for that. And you can also earn this by stating that the collision is inelastic. Because what does that mean? If it's an inelastic collision, kinetic energy won't be conserved. That's implied. And then you get for stating or implying that the system's kinetic energy has decreased. So 1 point, and you notice how they say or for calculating, because they allow you to solve these numerically as well. So you'd get 1 point just for saying that we actually went ahead and we decreased our energy. So if you remember, like our thought process and our explanation, we touched into a lot of these ideas, right? We talked about these things as we went through. But you have to explicitly state the kinetic energy decrease. And it says for stating or implying the kinetic energy of the blocks right after the collision equals the maximum potential energy of the spring. Or stating or implying the maximum potential energy equals the total mechanical energy after the collision. You could say that E total is equal to 1/2 Ka squared. So basically, where we went ahead and we said, well, the Ke max is equal to Pe max, right? Boom. That would have been 1 point right there. Then, for stating or implying that the maximum potential energy is reached when the displacement from equilibrium equals the amplitude of oscillation. Um, yeah, I stated this in an equation, but careful, you had to actually explicitly state that Pe max is equal to 1/2 Ka squared, right? Where the amplitude is related to that maximum potential. And then for a logical, relevant, and internally consistent argument that addresses the required argument or question and follows the guidelines described in the published requirements for paragraph length response. Basically, for something that stays consistent and doesn't contradict itself and follows a clear logical thought process would be 1 point. Now, they actually give you an alternate an alternate solution for the first 2 points in part B in saying that a frictional force is exerted on block P by Q, so it slows it down. A third point can be earned if energy loss is stated. So basically, just by talking about like when you land on something, if you stick, there needs to be some friction between those two objects, which would cause an energy loss. Um, you could state that as well, even though the surface itself was frictionless, the blocks were not. They had to stick. So I think if nothing else, and I know I kind of rushed through this without going through like our direct feedback, but that's because we just solved this question. If you realize we really had to be very explicit in hitting some of these key ideas. And in fact, if I had just missed out not stating, momentum must be conserved, not just saying, oh, it's a collision and the speed decreased, you would have lost 1 point right here. You have to apply the conservation of momentum. It has to be explicit, right? You have to correctly, identify the post-determined speed decreased. You had to explicitly state that the kinetic energy as a result decreases and that the kinetic energy is related to the maximum potential energy. And then you had to, very clearly identify that the maximum potential is related to the amplitude of the spring. Um, this AP kind of setup, guys, is very specific as they go through kind of the grading for a given solution. Um, all right, I think that's enough on that for now. I don't want to kind of overwhelm, and I'm actually going to stop our recorded lecture for now.